Welcome to Empowered Learning. This is the second video in the video series for derivatives and the info it reveals about a function. And so in the part one video, we went over basic concepts like we reviewed critical numbers, we reviewed what concavity is, what an inflection point is. But the main thing that we were trying to do in that video was to explain how using the first and second derivatives could be used to be able to help us learn information about the graph of our original function f of x. And so we culminated in talking about what the first derivative test and what the second derivative test actually does for us. And of course, both of them do the same thing, which is they both help us to find local max and local min, or relative max and relative min, if you refer to it that way. The first derivative test just uses critical values and test points around, or test values around a critical value plugged into the derivative to figure out, do we have a change in whether the function, the derivative of the function is positive or negative to positive. Okay. The second derivative test uses critical points or critical values, and it also uses the second derivative to be able to tell whether the location of where we have a potential local max or local min, aka the critical value, is it a local max or local min. Okay. Now, one of the ways that we could use the first and or second derivative test, and we'll mainly be using the first derivative test here, is to be able to sketch the graph of functions. And so I'm going to do three examples with you here where I'm actually going to kind of methodically go through the problems. I already have these worked out, and so by having them worked out, it'll cut down on the amount of time that this particular video will be, but I will go through each step to make sure that you see what's going on. Okay. All right. So in our first example here, you see that I have the title here, Template for Curve Sketching Using Applications on Derivatives. And so I make this template because there is a standard way, at least in my opinion, that we can go and attack trying to take a function and use the first and second derivatives to be able to draw the graph of. Okay. Now, this first example is one that is relatively simple. We could actually draw this particular function here by using the method that I used in the part one video to go over the polynomial in factored form example, just to try to remind you of some of the things that you need to carry over with you from pre-cal. But here we're going to see that we can actually accomplish drawing a graph like that by using first and second derivatives. And so what I'll do for this particular example, since it's a relatively easy one, we'll go through everything here and see how the graph ends up looking. And then I'll actually show you, if we did it the pre-calculus way, how we would end up getting a graph that looks similar. So the first thing that we want to do in dealing with our function before we start finding first derivatives and second derivatives is we want to identify some important things that we could know about our function. And we want to know about that so it'll make sketching the graph of it a bit easier. Okay. So for starters, we want to know things like what's the domain of this function. So I'm going to come and write up here. So the domain of this particular function, since it is a polynomial, is going to be all real numbers. Okay. And that's going to come into play in part of our template. Another thing that we need to know is, since this is a polynomial, can we find out where the X-Intercepts are? Okay. And here, if I factor out common factor of x squared out of both terms, we'll see that x squared times x minus 6, this function in factored form will let us know that, yep, we actually do have some X-intercepts. Okay. And X-intercepts are going to be located at x equals 0 and at x equals 6. Okay. And don't know why that's happening, but we'll fix that. All right, and so other than that, we know that since we're dealing with a polynomial, this has to be a smooth and continuous function. So we know that whatever it is that we draw is going to have to reflect that it's smooth and continuous for all real numbers. All right, so the first thing that we want to do after identifying this information here, and of course I'd already put the domain here, but I just wrote it again up here just to make my point. We want to find the first and second derivative. So for this polynomial function is relatively easy to do. We see that the first derivative of x cubed minus 6x squared is just 3x squared minus 12x. And I've decided to take the common factor of 3x out of both terms here to rewrite it this way. And the purpose of why I'm doing this will be apparent as we get further along in the template. When we take the second derivative, we're just taking the derivative of the derivative. And of course, that is 6x minus 12. And again, I factor out the greatest common factor amongst both terms. Okay. Now, from there, our goal is to be able to find out what our critical numbers, as well as our possible locations for an inflection point is. Okay. Now, notice that this says that we want to figure out when the derivative of this function is equal to 0, or what x values make that happen. Now, in actuality, we not only want to know when the derivative of this function is equal to 0, we also want to figure out when a derivative does not exist. Okay. However, in this situation, since we're dealing with a polynomial function, the derivative of a polynomial function is also going to be a polynomial, and polynomials are going to be defined for all real numbers. And so what that means here is that the derivative will be defined for all real numbers as well. So this particular problem, we won't see this case. Now, whenever we talk about possible locations for an inflection point, it's the same thing. We want to figure out when this is going to be equal to 0, or when we have a does not exist case. And of course, the second derivative of a polynomial is still a polynomial. And polynomials are defined and continuous everywhere. So we're not going to have the does not exist case here. So that's why you see me only looking at the first derivative equal to 0 and second derivative equal to 0 case. Now, you see here that the first derivative, I've written it out in factored form so that I can just visualize what the solutions to this equation would be. Okay, it's just going to be whatever values of x make each factor go to 0. Of course, for the first one, it is 0, and for the second one, it's 4. For the second derivative, we set that equal to 0. We're trying to find the location where we could possibly have a change in concavity. Okay, and a point on the graph of the original function where concavity changes is what an inflection point is. And so we see at x equals 2, that is the location that we are thinking concavity will actually change. And of course, since we're dealing with a polynomial function and it is defined and continuous everywhere, we know that it actually will be an inflection point there. We'll just have to find out what that corresponding y value is for this x value. Now, we have found the critical numbers as well as the possible location for an inflection point here. And so if we take all of these numbers here, this set of numbers here is what's known as partition numbers. Okay. And so what we're going to do with these partition numbers is we're going to break up our domain, which in this case is all real numbers, and we're going to study the behavior of our function by looking at the first derivative and the second derivative in each of these subintervals that we're going to make, and we're going to break up our domain into subintervals by using these partition numbers. And so I'm going to show you exactly what that looks like here. So on the next page, remember that our partition numbers are x equals 0, 2, and 4. And if you notice here, I've started at negative infinity, and everywhere where I hit one of my partition numbers, I make an open interval with it, okay? Now, what you see here is me using test values to plug into my first derivative and second derivative, and you see that I have these outcomes here. I'm going to spend a little time to explain how we actually came up with these outcomes. So how we got these outcomes here in this column that says f prime of x, and really this is trying to figure out whether our original function is increasing or decreasing, and the second derivative is to find out whether our function is concave up or concave down in that interval. We take our first and second derivative of this function and we plug in these test values. The test values come from just random values that we select inside of each of these intervals here. And so the idea is that however this function acts, however the first derivative and the second derivative acts at this test value, it will act for all of these values within this interval, okay? And each test value is just a representation of how the first and second derivative will act for all values in that particular interval. So what we're going to do is see how we actually came up with these outcomes here. All right, so how we come up with these particular outcomes is we are going to plug in all these test values into our first and second derivative here. And of course, the idea is for us to be able to figure out whether the result is going to be positive or negative, okay? So for example, we'll go with the first derivative. Let's say the first derivative evaluated at -1, because that was our first test value. Here, if I was to plug in a -1 in for x here and a -1 for x there, then 3 times a -1 is a negative number. Notice that I'm not trying to figure out what the actual value is. I just need to know whether it's positive or negative. So 3 times a -1 is a negative number. -1 minus 4 is a negative number. And a negative times a negative is a positive. Okay? If I do this with the second derivative, I know here that because I have a 6, this is always going to be positive. So I got positive times a negative, that's going to be negative. Okay? And of course, we can continue on and do the same thing with all of our other test values. And I'll go ahead and run through it here so that you see how this works. In the other examples, I won't necessarily go through this step here. I'll just assume that you know how to plug values in and tell whether the result for the following factors are going to be positive or negative. So for this next one here, we had a test value of 1. And of course, if I plug in a 1 here and a 1 here and a 1 here, then for the first derivative, 3 times 1 is a positive number. 1 minus 4 is a negative number, and my result is negative. And for the second derivative, of course, I got a positive number times a negative number again, which would be negative. Repeating again, for when x is 3, we'll see that, let me get rid of these 1s and put 3s here. Okay, so here 3 times 3 is a positive number. 3 minus 4 is a negative number. So the result ends up being negative when I multiply them. Next, I have a positive number times 3 minus 2. That is a positive number. So now this finally changes to positive. And then I have one more to do. First derivative evaluated at 5. Get rid of this and write 5s in place. So 5 times 3 is a positive number. 5 minus 4 is a positive number. So that result is positive. We'll do the same thing with the second derivative. Of course, 6 is always positive, and 5 minus 2 is positive. So that result is positive here. Okay. And so what this means now is, if you recall, when the first derivative is positive for a particular x value, that means our original function was increasing at that particular x value. So what this essentially means is that for this first interval that we had, our function's increasing. For the second interval, it was decreasing. For the third interval, it was decreasing. And for the fourth interval, it started increasing again. Okay. Now, as far as the second derivative is concerned, we know that when the second derivative is negative, that means our graph is concave down. So it'll look something like this maybe. Okay. When the second derivative is positive, it'll be concave up. So it'll look something like this maybe. Because there are other ways that it can look concave up. And I went over that in the part 1 video. Okay. And that's still not a good looking C here, but hopefully you get the point. All right, so for the second derivative, we know that negative means concave down. So this is, pen is not acting right today. So this is concave down, and then it switches to concave up and concave up. And so if we go back to the notes that we had, and what you see here is that the outcome that we got in this first column, which is plus, minus, minus, plus, is the same outcome we got in the over here when we did this work. Positive, negative, negative, positive. Okay. Now you also see in the second column we got negative, negative, positive, positive. And of course our result here is negative, negative, positive, positive. And so what we see here is that, again, anytime in this column with the first derivative, positive means increasing, negative means decreasing. In the second derivative, negative means concave down, positive means concave up. And so now that we have this, the next thing that we need to pay attention to here is precisely those questions that we talked about in the part 1 video. When is our function increasing? When is it decreasing? As well as when does concavity change? Okay. But we also had questions of where do we have a relative max? Where do we have a relative min? And so this chart also shows us that information as well. So if we look a little closer here, we'll use a different color, notice that from this interval to the first interval to the second, notice that we go from increasing to decreasing, meaning we go from having positive tangent line slopes to negative tangent line slopes. In that case, we see that we have a local max here. So at x equals 0, we see that we have a local max. Okay. We also see from our chart that we go from decreasing to increasing from the third interval to the fourth interval. And of course, all that action is around x equals 4. So we see we go from having negative slopes of tangent lines to positive slopes of tangent lines, which means we have a local min at x equals 4. Okay. Now for the second derivative column, what we care about is when concavity changes. And we see that that happens in between the second and the third interval here. So what that tells us is that all the action is around x equals 2. And just as we predicted on the previous page, we know that we should have a possible inflection point here at x equals 2, okay? And we know it's actually going to be an inflection point because, again, our function, since it's a polynomial, is going to be defined for all real numbers, so it'll definitely be defined at 2. So at this point, what we need to do is find out what is going to be the corresponding y values for x equals 0, x equals 4, x equals 2, okay? And so here you see that I have already plugged in that information and found that out. In addition to that, I have went ahead and placed each of those points where they need to be as far as what's going to be the local max, local min, or relative min, relative max, and inflection points. So, of course, that came from these numbers up here, x equals 0, x equals 4, x equals 2. And we just found the corresponding y values for them, which is here. And so now the graph that we end up having as a result just looks like this. And so I'm going to go over the chart so that you can see how we can actually come up with this graph, okay? So for starters, since we already know these points here, we can identify them on our graph. So here, I'm going to use blue here for that. So we know we have the point 4, negative 32, which have this point here. I have the point 0, 0, which I have here. And I have the point 2, minus 16. Now, again, since we have a relative min or a local min here, we know this is going to be a dip in the graph. So it goes from negative tangent slopes of tangent lines to positive slope of tangent lines, okay? So we know that there's going to be a dip in the graph here, okay? For the relative max, we know it's at 0, 0, okay? So we know there's going to be a peak in the graph here. And just by looking at what we see here and here, we know that our graph's going to have to decrease in between x equals 0 and x equals 4 because of the fact that our function is a polynomial. So we know that in between here, the graph is going to have a negative slope of a tangent line, okay? In other words, it's got to be decreased. Now, if we go back to our chart here, we will see that for this first interval from negative infinity to 0, our graph is increasing and it is concave down, okay? So graph increasing means it has to go up. Concave down means it's got to kind of look like this, okay? And so if you remember off the part 1 video, one of the ways I describe concave down is you pour water on the function, the water rolls down. Concave down, water rolls down. Whereas concave up, water settles in the cup whenever you pour water on it, okay? So here we know that for this first piece of our graph, as you can see, it meets the condition of what I've been saying before. From negative infinity to 0, the graph has to be increasing but yet concave down. If we go back to the chart for the next interval from 0 to 2, notice that our function now is decreasing, but yet it's still concave down, okay? And of course, notice that our function still decreasing here. Sorry, it starts to decrease, but yet it's still concave down. So we got all this here, okay? And then of course from 2 to 4, we said that the graph of our function in this case was still decreasing, but now it switches to being concave up. And of course, where this switch in concavity happens is where our inflection point is. And now we know what the inflection point is actually the point 2, negative 16. And thus, that's why we have this particular point here. And I'll just do it in different colors to make sure that got it now. So we have that. But we also know that the graph was decreasing and now concave up. That happens till we get here. And then, of course, the last line in our chart says from 4 to infinity, graph has to be increasing and also concave up. Okay, so increasing, concave up. So if we look here, we see from this point here, and let me switch colors again. So from this point here, graph has to be increasing and concave up. Okay. All right. So we see that this particular graph here, it's going to have this general shape. So now what I'm going to do, just as a sanity check, is to do this pre-calculus way, so that you see that we have basically the same graph. It's just that there are certain things that we will know about doing it the derivative way that we won't necessarily know doing it the pre-calculus way, and vice versa. All right, so if I was going to sketch a graph of this particular function here, doing this the pre-cal way, then the first thing I would do is identify where my X-intercepts were. And just looking at it, I could tell that that's going to be at x equals 0 and x equals 6. I would need to know the multiplicity of each 0. That's how many times a factor repeats. I have a factor of x repeating twice, and I have a factor of x minus 6. It only shows up once. Now, whenever our multiplicity is even, we know that the graph is going to bounce off of, or that is to say, touch the x-axis. The proper way to say it is tangent to the x-axis here. Whenever the multiplicity is odd, it's going to cross through the x-axis. All right, and so now that we have all that information, the next thing that we need to do is figure out what the degree of this polynomial will be. And of course, we already know that it's 3 here. But if we add up the multiplicities, we see that we still have that. And we also need to pay attention to what's called the leading term, the a sub n term. And of course, here there is an understood 1. And so what that tells us is that for very large values of x, this graph, this function here is going to act like x cubed in its in behavior. And so that essentially means here that its in behavior for very large values of positive and negative x is just going to be like this. So now when we put all this together, we say that we have x equals 0 here. I'm just going to say x equals 6 here. And we know that our in behavior is going to have to look like this. And so now we know that if this function is smooth and continuous, it's going to have to come from down here up here, and based off of the multiplicity, is going to have to bounce off of the x-axis. At x equals 6, it's going to have to cross through. So this graph is going down. It somehow has to come back up and then cross through here so it could touch this part. Okay. And so now when we connect the dots and put everything together here, our graph is going to look something like this. Okay. Now notice that in the sketch of this graph, some of the things that we don't know, that we haven't specified is, I haven't specified how low does this go, meaning where's the local min. I also haven't specified this point here, that's the inflection point. Didn't care to know about that, okay? Now, if you notice in the other graph that we have, I do know where the inflection point is. I do know where this local min is, okay? I also know where this local max is, but note here that I already had that just because the origin was also an x and y intercept. The other thing that you don't see here is that I have not graph this function to where I have the other x-intercept at x equals 6 clearly graphed here on this particular graph. I didn't do that, but of course on here I did. Okay, so this is some of the differences that we can see in actually using the derivatives to be able to sketch graphs versus using the ways that you learn in pre-cal to be able to sketch graphs of these types of polynomial functions here. Okay. All right, so let's move to our next example. All right, so for our next example here, we have a rational function, and this one's a little bit more involved. So some of the things that we would like to know about this function that's sort of pre-cal based is, does it have any x-intercepts? Does it have any vertical asymptotes? Does it have any horizontal asymptotes? Is a function going to be even or odd or neither? Okay. All these things help us to be able to make an accurate sketch of what this particular function's graph would look like. Okay, so notice here, because the numerator only has x in it, that lets me know that x equals 0 is going to be the only x-intercept I have. Since x squared plus 9 can never be 0, no matter what real number value for x you plug into it, I know that we're not going to have any vertical asymptotes, as many rational functions do. Okay, so because of that, it's going to make this function look a little different than some of the normal rational functions we're used to seeing in pre-cal. Horizontal asymptote. We know we have one at y equals 0 because the degree of the numerator, which is 1, is smaller than the degree of the denominator, which is 2. Okay. And lastly, I know that this function is odd because if I do the algebraic test for it, if I plug in a negative x everywhere where I see x, I get the negative of what the original function was. Okay. Now again, all that matters because again, if a function's odd, if I have a point x, y on this graph, then that means that I automatically know that there is a function negative x, negative y on this graph as well. So let's say if I had the point 2, 3 on this graph, then that means I automatically know I also have the point negative 2, negative 3 on the graph as well. And so what this essentially means is if I can figure out what one half of the graph looks like, I can tell you what the other half is going to look like. Okay. All right. So after noting all that pre-cal information, we need to figure out what the first and second derivative of this particular function is. Now, for this function, I could have chosen to rewrite this as x times x plus 9 raised to the negative 1 and use the product rule. But of course, in the product rule, I was going to have to use the quotient rule in some steps. So to me, I was like, well, it's probably better that I leave it in quotient form because I'm probably going to have to use the chain rule at some point in doing all this anyway. Okay, not necessarily for the first derivative, but I know for the second derivative I will. The main thing that I want to show you here is after we employ the quotient rule to find out the derivative. Of course, I'm just doing low d high minus high d low over low squared. And that's what this first outcome is here. Then, of course, the derivative of x is just 1. Derivative of x squared plus 9 is 2x. Simplify. And this is what this would be once I'm done simplifying. But I want to step further here to factor out the numerator because that's going to help me out later on when I need to find out, well, when is the first derivative going to be equal to 0? I'll quickly be able to look at the numerator and tell that it's just at x equals 3 and x equals negative 3. Okay. Now, notice that I have this rectangular box around this version of the first derivative. And I have that because we're going to use that to find out the second derivative here. Okay. And so the second derivative, if I take the derivative of the derivative, it's the same thing. I have the quotient rule. So I have low function times derivative of high minus high function times derivative of low, all over low function squared. And you see that when I do that, I end up getting what's in this step. Next step, I actually execute the derivatives. So here, when I have to take the derivative of the high function, that's just minus 2x. When I have to take the derivative of the low function, I have to use the chain rule. And so that'll be 2 times x squared plus 9 times the derivative of the inside function, which is 2x. And of course, x squared plus 9 squared is just x plus 9 raised to the 4th. Now, at this point, one of the things that I'm going to encourage you to do, and you see me do it here, is all terms that have a x squared plus 9 in it, we want to try to leave those in factored form, okay? So you see how we have this x squared plus 9 squared? I want to leave it like that. I have this factor x squared plus 9. I want to leave it like that, okay? And the reason I want to leave it like that is because since I have x squared plus 9 raised to the 4th here, if I have any common factors of x squared plus 9, I want to factor it out. And so here at this step, I'm just kind of rearranging things and just rearranging things. And so here I see that I have 1x squared plus 9 and I got 2x squared plus 9s here. So I can factor at least one of those out, okay? So when I do that, I have a minus 2x, and then I have an x squared plus 9 left. Then I have minus 4x times 9 minus x squared. And of course, this is the only x squared plus 9 here, so it doesn't show up anymore. This x squared plus 9 that we see in the numerator is going to not cancel, but reduce to 1 with one of the 4 x plus 9s we have here. And so we have x squared plus 9 cubed. And for the rest of this business here, we go ahead and distribute so that we can combine like terms here. So we see what the numerator looks like in this step. And once we simplify it, it'll just be 2x cubed minus 54x. We have a common factor of 2x here. And so when we do that, we see that we end up having 2x times x squared minus 27 in the numerator. And of course, and I kind of go through this the long way, but we know that square root of 3 times 3 squared here is just going to be 27. So that's what I'm trying to show here. And of course, I have it in this form of x squared minus a squared. I'll write this here. I have it in this form so that we know that this simply just factors to x minus a times x plus a. And we're going to see that later on when we start to solve when the first derivative is equal to 0 and when the second derivative is equal to 0. All right, so for this particular problem, this is probably the second hardest part, just getting the derivatives. And so now once we put everything together here, again, we have x squared plus 9. Let's see, for this first derivative, let me come back here. This x squared plus 9 will never be 0, so we're not going to have any cases where the derivative does not exist. But we do have both positive 3 and negative 3 if we plug that in for x in the numerator, where it will go to 0, okay? And for the first derivative, the x values that make the first derivative go to 0 is what our critical values are, okay? And so you see that that ends up being the case here. So x is equal to plus or minus 3 for the first derivative. If we were to now work on the second derivative, again, no value of x here will make the denominator equal to 0. So we're not going to have a does not exist case for the second derivative either. We just look at the numerator here to figure out where f double prime of x is equal to 0. And we can look and see that x either has to be 0 or plus or minus square root of 3 For the second derivative, it'll go to 0. And so here, what you see is that these are going to be the potential locations for our local max and local min. X equals 0 and plus or minus square root of 3 are going to be the potential locations for inflection points. And all these numbers together will be used as what we call partition numbers, or numbers that we're going to use to break up the domain of our function. So we're going to look at that next. So here, if you see, and I'm going to drag this down some, we see that we use all these numbers here to break up the domain of our function. And again, the domain of our function is all real numbers. So we start at negative infinity, end at positive infinity. And we start from most negative number, that's a partition number, to break up the domain until the most positive. So the most negative is negative 3 times square root of 3. And just in case you don't know here, plus or minus 3 root 3 is about plus or minus 5.2 roughly. Okay. So in looking here, just like how we did for the first example, I picked test values that are in each of these intervals, and then I plug them into the first derivative, and I plug them into the second derivative. And the outcome that I want is to see is the outcome when I plug in those x values into the first or second derivative, is it going to be negative or positive? Okay. For the first derivative column, if my result ends up being negative, I know that the graph is going to be decreasing for that interval. For instance, here we see that since test value of -6 plugged into the first derivative ended up giving us a negative value, that means the slopes of the tangent lines for points in this interval here, according to the function, will be negative, so the graph is decreasing. Whereas here, we know that plugging in a -1 into the first derivative made the first derivative a positive value, so therefore our particular function is increasing, or has points that have tangent lines that have positive slopes. Okay, that's another way to put it. Of course, for the second derivative, if we get negative value for this test value, then of course it's concave down. If it's positive, then we know it's concave up. And so I'm going to quickly show you this here, that I have my function here for the first and second derivative. And notice how I've used all these test points and I've just plugged it in. And so I was a little bit more direct this time in actually showing you what the actual values were. Again, this is not needed. All you need to do is be able to figure out, is the result going to be positive or negative? Okay. So for example here, for f prime of -6, I know that if I just would have plugged in a -6 here and -6 here and -6 here, anything squared is always going to be non-negative. Okay. And since x squared plus 9 will never be 0, I know that no matter what number I plug in down here, it is going to be positive. So I can really ignore the denominator here because I know it's always going to be positive. And so in this case, the numerator, 3 minus a -6 is a positive 9, and 3 plus a -6 is a -3. And of course, when I look at all of that, a positive times a negative is a negative, negative divided by a positive is a negative, and you see that's how we got that value. Okay. And if we keep doing this for each of these values, you'll see that we get everything that you see here. Okay. And of course, that is what these outcomes here in the f prime of x column and the f double prime of x column ends up being. Now, just like how we did before, we could read this chart here, and this chart will let us know how the graph is going to look for this interval of x values. And so I'll start off with the first few, and then I'll leave the rest for you to kind of figure out here. So for this first interval, we see that because this is negative, our function is decreasing. and our function is concave down. So decreasing and concave down is going to look something like this, okay? So if we go and look at our graph here, and I'm going to skip talking about the relative min, relative max, and inflection points for now. If you look at our graph here, notice that our graph from negative infinity to negative 3 times square root of 3, which is at this point here, so that's corresponding to x value. Notice how the graph is decreasing and concave down, okay? Also note how I noted here that I have a horizontal asymptote at y equals 0, okay? Now that's important because I know that for values of x that are getting more and more negative, I know that my y values are getting closer and closer to 0. And I need to be able to communicate that on my graph as well, okay? Even though it has nothing to do with the derivative, we do need to communicate that. And so that's why our graph here to the far left starts to kind of flatten out, because for very large values of, well, I'll say for, very large values of negative x, meaning the more negative we get. I mean, I know that's technically incorrect terminology, but hopefully you get what I mean. The more negative or to the more left we go here, we see that the corresponding y values get closer and closer to 0, okay? All right, and so, of course, here at this particular value, if we go back up to our chart here, at the negative 3 root 3, notice that we have a change in concavity, okay? And so we see here that that's why our graph goes from looking like it's a concave down type situation over here to now it's looking like it is concave up. And of course, it'll continue to be concave up until it gets to this point 0, 0 here, okay? And so just like how we did before, now that we've kind of gotten a little deeper into the graph, we can figure out where our local max, local min, and inflection points are just by looking at our chart. So we can see here, since concavity switches, we know that at negative 3 times square root of 3, we are going to have an inflection point. Because again, we know that our original function is going to be defined at any x value because its domain is all real numbers. We see that concavity switches again here. And so if we kind of look down, that's going to be all the action is around x equals 0. So that's going to be another location of an inflection point. And it switches again one more time here. So positive 3 root 3 will be another inflection point. So as far as relative max and relative min, if you notice here, we have a switch here going from decreasing to increasing. So that tells us that we're going to have a local min right here at x equals negative 3. And we also see that we have increasing to decreasing happening here, which means at x equals positive 3, we have a local max. Okay. And so here, of course, we've noted the places where we have a local min, a relative min, and a relative max or local max, as well as all the places where we have an inflection point. And of course, down here, I've just taken the time out to calculate what all the corresponding y values are to these x values that I have here. Okay, so that's what all this information is here. And then of course, after that, reading the chart like how I was showing you, if we do that for each interval, we'll see that we end up with a graph that looks like what you're seeing here. And noting that as x goes to positive infinity, this graph here is going to ride along this horizontal asymptote y equals 0. okay? And so from that, we're using everything that we know from the first and second derivative here to be able to get a more accurate sketch of what the graph of this function would look like. All right, so now let's get into our third and final example. All right, so for this last example here, I'm going to go through it a little faster than I did the others, just because we should be kind of familiar with what's going on now. Hopefully you're starting to see that this process is not hard. It is somewhat tedious, but it is not hard, okay? In this example here, I decided to take my rational function that I have and, of course, write it in factored form, but I decided to write it to where I could use the product rule instead of the quotient rule. Okay? And I wanted to do this for this example just to appease those people who would prefer to take the derivatives of these rational functions this way versus doing it the other way that I did in the second example. Okay. So, of course, it's the same deal again. I need to take the first derivative of what I have. And of course, now I'm using the product rule here. Before I get into that, though, let me go ahead and mention this, even though I mentioned it later. We recognize that we're going to have X-Intercepts or an X-Intercept at X equals 3. We also see that because of what we're looking at here, we are going to have a vertical asymptote at X equals -2. Okay, so we also see that. We also see here that since degree of numerator is smaller than degree of the denominator, that we're going to have a horizontal asymptote. We're going to have a horizontal asymptote at Y equals 0. And I'm not sure why that's acting that way, but okay. So we have all that. That's important for us to know as well. So again, of course, we take the first derivative. You can kind of see how I'm using the product rule here. Once I actually execute everything in this step, it's just a matter of me trying to rewrite it to get it in quotient form. And I do that here. And I want to do that and use this form of the first derivative to be able to tell when the first derivative is going to be equal to 0. Okay, what values of X are going to make that equal to 0. And you can quickly see here that in this form, X equals to 8 will be that number or that critical value that we would be looking for in that case. And again, the critical value would be the place where we would have a potential peak or dip in our graph, or to put it formally, it's a place where we will either have a local max or a local min in our graph. Now, after I noticed that here, I put this back in, of course, negative exponent form for the denominator, so I can take the derivative of the derivative by using the product rule again. And of course, you can kind of pause the video and kind of look at all my steps and see what I'm doing here. But once we're done actually applying the product rule, and of course, in this last little part here, the chain rule as well, again, I'm just rewriting everything to get it into a form that's like a quotient, because that's advantageous to me to figure out where the second derivative is going to be equal to 0. And I see that this is my final result. And I can quickly see here that at X equals 13 is going to make my second derivative equal 0. Okay. Now, the other thing that I want to mention here is that notice that for this rational function is different than the last one that we had, in that we now actually have a vertical asymptote. Okay. So we know we have a vertical asymptote, and that's fine. But there is a potential for this graph to switch concavity at that vertical asymptote. It also has the potential to switch from a graph that is decreasing to a graph that is increasing and vice versa, okay? So because of that, one of the things that we need to consider here is not only when does the first and second derivative of our function equal 0, we not only need to look at that like I've done here, but we also need to look at when is the first derivative not going to exist and when is the second derivative not going to exist, okay? And for this one, it's relatively simple, so that's why I left it out. So here I know that this will occur at x equals -2, and I got a vertical asymptote there, okay? So because I have a vertical asymptote here, I know it's not going to be a local max or a local min there, so no local max or min here. Because again, x equals -2 would be an undefined location on the original function as well. If I look at the second derivative and try to figure out where that does not exist, and again, that's going to be at x equals -2 because we have a vertical asymptote there and there'll be no inflection point here, okay? So I didn't write it in here because we knew, all right, there was a vertical asymptote there, but if we're going to be formal about it, we do need to at least recognize it, okay? All right, so from this point, we know that x equals 8 and x equals 13 is going to be our partition numbers. The domain of our function is going to be all real numbers except for -2. And so since -2 is where we have a vertical asymptote here, there's some action happening there. We want to include x equals -2 as part of our partition numbers, okay? So the three numbers that we're going to use to break up this particular interval, the domain of our function, which will be our intervals, is just going to be, of course, -2, 8, and 13. And of course, -2 will naturally be broken up because we have a vertical asymptote there. Well, it'll naturally be used as a partition number because of that. All right, so if we go to our test intervals, we see that, again, I've started partition numbers -2, 8, 13. And so started at -2, then to 8, and then to 13. And just like how we did before, we took our first derivative and second derivative. Let me go back up here. We took our first derivative and second derivative. We plugged in those values of x into them, meaning our test values that we picked. So we plug all these values here, 3, 0, 10, and 14 for each interval respectively, and plug it into our first and second derivative to see the outcome. Here, I'm not going to go through that again this time. We see that that's what the outcome ends up being. For the first derivative, going from interval to interval, it'll be negative, positive, negative, negative, which means our graph for the interval from -infinity to -2 would be decreasing. For the interval from -2 to 8 will be increasing. The interval from from positive 8 to positive 13 is decreasing. And then from 13 to infinity will also be decreasing. For our second derivative, we have negative, 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 positive, which means that for the first three intervals, we're concave down. And for the last one, we are concave up. And so looking here, once we know all that information, I know that at x equals -2, 8, and 13 is where all the action is. So I need to figure out what's going to be the corresponding y values there. Notice here at this time, I actually wrote down, hey, I have a vertical asymptote at x equals -2, horizontal asymptote, y equals 0, and where my x and y intercepts were, because it's going to help me to be able to graph a sketch of my function a little bit better. And then from that, we just use the chart. And this chart will help us to not only figure out where our relative min, relative max, and inflection points are. And of course, we knew about the I guess the relative min part is really a vertical asymptote, so this really doesn't count here. But our relative max, if we go back up here at x equals 8, notice here, and I'm going to switch colors. So notice here that at x equals 8, what happens is we go from increasing to decreasing. So we go from having positive tangent line slopes to negative tangent line slopes. So that lets us know we have a local or relative max here. Okay. And of course, at 13, the big thing here is that concavity switches. Okay. And so that's how we know we have an inflection point at x equals 13, relative max at x equals 8. And of course, we've already found the corresponding y values to go with that. So when you read that chart, you'll see that this is what corresponding graph ends up looking like. Okay. All right, so I wanted to quickly go through just one more example. I'm not going to go through it as detailed as I did this one, but I do want to show you some, at least one example of some functions where it can get a little tedious, but it's really what this process is made for as far as using first and second derivatives to be able to sketch a graph of a function. And I say that because for all the examples that we've done here in this video, we could have done them the pre-cal way. I want to show you at least one example to where there is no pre-cal way to do it. We're going to have to use these techniques to be able to sketch the graph of this particular function. All right, so this is an example of a function to where there is no real pre-cal way to try to make up a quick sketch of it. We're going to have to use first and second derivatives to help us out here, okay? And notice here that since I know that natural log of x domain is x is greater than 0, and square root of x in the denominator would have a domain of x is greater than 0. I know that the domain of this function is only going to accept positive numbers. And so thus, I go through the process of finding the first derivative, which is this. Do that again to find the second derivative, which is this. And now what we need to do is figure out when is the first derivative and the second derivative going to be equal to 0 here, okay? And notice that I have this note here that this function also is going to have a vertical asymptote at x equals 0, and it's going to be undefined for all values that are 0 or negative, okay? And so I know it has a vertical asymptote because of the fact that, because of the fact here that natural log of x, as x gets closer and closer to 0 coming from the right, approaches negative infinity, okay? And of course, this value here, as it gets closer and closer to 0, its value is going to get smaller and smaller as well. So I got a number that's approaching a very large number divided by a very small number, which is going to get even larger, okay? All right, so we take the first derivative and second derivative. We're going to set them equal to 0 in this case. We already know the instances to where the derivative is going to not exist. And of course, that's going to be for any value of x that is 0 or negative. So we don't have to worry about that since we're only dealing with x values that are positive. We take what our first derivative and second derivative are, set it equal to 0. And of course, we go through the whole thing of trying to figure out what values of x satisfy these equations here. And so you have to remember how to be able to solve fractional exponent equations, or what they call nth root or radical equations, as well as your logarithmic and exponential equations here. And so you see how that works out for both the first and second derivative. And you'll see that we have a critical value here of e squared. We also have a place where we would have a possible inflection point here at e raised to the 8/3. And so these will be our partition numbers here. And of course, our interval that we will be considering is from 0 to infinity. So from 0 to infinity, and of course we break it up using the two critical values that we had, which is, sorry, not critical values, but the two partition numbers, the critical value e squared, and then the other value that we use for locating the inflection point, which is e raised to the 8/3. And of course, I've given you the decimal approximation of that. Now, to test out these values here, I keep everything in terms of e because it actually makes it easier for me to figure out what it is that I need to know, since I have a bunch of natural logs in these functions. I know that natural log of e is 1, natural log of e squared is 2. So by keeping it, in those terms, it actually makes it easier to evaluate the first and second derivative here. So I pick test values accordingly, and you'll see that I get this result here for the first and second derivative columns. And you'll see here how by using the first derivative and keeping everything in terms of e, how it makes it relatively easy for me to figure out, whether the first derivative is going to be positive or negative at those test values. Okay, and then of course I do the same thing for the second derivative here. Looks a little bit more involved, but of course, once you actually go through it, you'll see that it's really not that bad. Okay, just takes a little more writing than what we would like to do. So from that point, we use that chart, and the fact that we know that chart lets us know where we have a relative min, relative max, and inflection point. And of course, in this case, we do not have any relative minima or local mins. And we see that our graph ends up looking like what you see here. Okay, and now the only part that you really don't see is that for very large values of x, this graph is going to kind of go like this. Okay, and eventually the graph is going to ride along the x-axis, meaning that we're going to have a horizontal asymptote there. And the reason that I know that is if we go back to our original function here, if you look at a graph of natural log of x, and then you look at a graph of square root of x, you'll see that square root of x gets bigger than natural log of x relatively quickly. Okay, so we know here square root of x looks something like this, whereas natural log of x looks something more like that. Okay, so square root of x is growing much faster than natural log of x here. Okay, so and we know that. So over time, the denominator here is going to grow much faster than the numerator, and so any number divided by infinity is going to give us 0. And so hence that's how we know over time, or I shouldn't say over time, but as x gets closer to infinity, we're going to actually have a horizontal asymptote here on the x-axis, and it's going to be one-sided. We wouldn't have that horizontal asymptote over here because, of course, for all values of x that are 0 or negative, the graph is undefined anyway. Okay. All right, so I have several other examples I could show you, but it would just kind of be overkill at that point. Hopefully these 4 examples have given you a good idea of how we use the first derivative and the second derivative, and mainly using the first derivative test, because that's what we were doing in the charts here. And just to be clear, this column here, we were using the first derivative test. And in this column here, we were using the concavity test. Okay. So those are the 2 main things that we used here to be able to figure out what we needed to know to sketch the graph of these functions here. And again, hopefully these examples have helped you kind of see what's all involved in it and helps to give you a systematic way of doing these for yourself. All right, take care.